So yeah, the day of Pi Day, we'll be having a math talk, and you'll see details coming up on our website soon. Best way to stay up to date on programs is just to go to the home page, and this is where we'll post all the latest stuff. And we do have Kopernikids back as well. And Kopernikids are STEM programs for ages 3 to 6. So it's this introductory set of classes. And the spring programs are almost sold out, but there's still a couple of slots left in some of the classes, so worth checking out. And you can register online, super easy. If you want to review what we did during the fall and all the events we had, including our 50th anniversary, you can refer back to the Kopernik Constellation, our newsletter. Our current plan is to have a fall and a spring. We'll see if we can get around to a summer as well, though that is a very busy time of year. So a lot of the events will probably end up in the fall 2025. Since I mentioned the 50th anniversary, we kind of closed out the 50th anniversary with Winter Star Party last week. That was March 1st. And among the things we did during the 50th anniversary was unveil this time capsule, which is why, if you're wondering why there's this hole in the wall, that's what that's from. And if you want to come up later, you can also see the stone, the founding stone for when Kopernik was first built. This was the original exterior wall of the building. And this founding stone now says Kopernik Observatory 1973. So that's been re-engraved, and we're going to return both the items that we found in there and new items to the time capsule. And if you're interested after the program, we can show you some of what's going in there. We kind of have it stacked up in the back, so I'd be happy to show you that. So now we're really looking ahead into the future and to what Kopernik can become over the next 50 years, and hopefully even sooner. So last thing I'll show you on the website is the clear sky chart. And the clear sky chart shows you an astronomical outlook of the forecast. And ultimately what you want to see here is all dark blue. And earlier today we had some dark blue. Now we're kind of fading into this poor, especially with transparency and seeing it's really bad. We might be able to get some of the brighter stuff peeking through, like Jupiter, for example, as the night goes on. So yeah, we'll see how that behaves. Tomorrow night's looking pretty good, beyond seeing. So yeah, you can see during the nighttime hours, nice clear skies. So yeah, our Fridays and our events are just not syncing up. I know winter skies was pretty cloudy as well, but we'll see if over the course of spring we get some nice clear skies on Friday. All right, so that's a bit on the website. Last thing I'll show you here, and last thing I'll plug, I guess, is the Kopernik Observatory YouTube channel, where you can tune into events like this. So we're live streaming now. You can see it says live here for our Spring Skies program. But we also do observing live streams, and I'm hoping that we'll be able to get out a live stream this coming week, which we'll talk about what events going on there. The observing live streams are effectively we hook a camera up to a telescope, or just have even a wide field camera fixed on the sky, and we observe. Cameras end up being a lot more sensitive to light and these objects in the sky than the eye, so you get a lot more detail out of it that way too, and kind of compare and contrast between visual observing versus camera-based observing. So that's a great resource for you as well. Even if you can't make it up here, there's always a place where you can tune into Kopernik events. All right, we'll jump over here now to tonight's main program. Okay, so yes, tonight we are talking spring skies. And my name is Cartie. I am Kopernik's live stream astronomer. So you would find me on the YouTube channel there during observing live streams. I'm also one of the educators here and the technology manager at Kopernik. So we're going to take you through what's out this time of year, and I'm trying to get rid of that little toolbar at the bottom. There we go. Okay. So this picture in the background here was taken fairly recently, I think last spring, at Kopernik Observatory. So you can see that that's our overhang there. Yeah. Yep. All right. So what are we talking about tonight? Well, we are going to review the ABCs of stargazing. Raise your hand if you know your ABCs of stargazing. Okay, we're going to go through them again then. So what can we see in the sky? That's the big one. And then closing out with observing tools that you can use both here at Kopernik and at home. So let's get into the ABCs of stargazing. So this A is for angular size and distance. Now that sounds a little scary at first, but all we're talking about is how can we measure, I'll show you a really simple tool we can use to measure the distance between objects in the sky, because that offers a point of communication when you're observing with someone. It gives you some context. It's not just a look here in the sky. It's, okay, how far away is this object from this object? Even how big in the sky is a particular object. So let's go forward. And this is the tool you can use. It's a handy trick. So we measure an angular distance, which is degrees. And we'll just go through each step together. The only way this works, though, is with your arm stretched out. So arm stretched out, and you just go through those different gestures. And so pinky out, the width of your pinky is 1 degree. Okay? Now, if you held your pinky up to the moon, you could even do it with the sun, but the sun is less safe. We're going to talk a little on solar safety later, but let's just focus on the moon. They're very similar in size. So you would be able to cover up the moon with your pinky. The width of your pinky will be bigger than the moon is in the sky, which should tell you the moon's pretty tiny in the sky. It's definitely the biggest thing that we can see in the night sky. Biggest, I should say, terrestrial object. And it's the most noticeable, but that's just because everything else, like the stars around it, the planets, they're pretty small in comparison. And another trick with this, you could test that. The true size of the moon in this case is about the width of your pinky nail. You could measure it at the horizon, and you can measure it high up in the sky. It's going to be the same size. The apparent change in size of the moon when it's close to the ground, apparently close to the ground versus high in the sky, it's all an illusion. You could test it with a dime too. A dime is held at arm's length, is about the size of the moon as well. Okay, so that's your 1 degree. Maybe we can measure 3 degrees with 3 fingers together like this. 3 degrees in the sky. Oh, sorry, 5 degrees, thank you. 5 degrees in the sky. Then 10 degrees is a fist. And 15 degrees, your index finger and your pinky finger kind of spread out a little bit. And then you can go through and measure the distance between objects. So as an example here, we have the Big Dipper and the degree measurements between the stars of the Big Dipper. That's a really good one to practice on. Like if you want to take your phone out and take a picture of this slide, just to remember the degree measurements. Next time you see the Big Dipper, you could practice with this. That would work really well, because the Big Dipper is very noticeable. All the stars are very similar brightness, so it's easy to pick out. Just look north. And this time of year, the Big Dipper is really going to start climbing up in the sky. And we'll talk about why that's important too. Okay, so that's the A, measuring distances, angular distance. Now, B is for brightness. And in astronomy, we refer to brightness as magnitude. So we think the magnitude of objects, and we can place them on a number line like this. And you're going to notice right away we're going from negative numbers to positive numbers. But it's kind of inverse to how you'd think about it. It's not intuitive. You have negative numbers on the left side, positive numbers on the right side. Very bright is on the left side, very faint is on the right side. So the sun's, actually I gotta remember I have this little pointer. The sun's all the way over here. And then the faintest objects are all the way over here. We can go through this line. The full moon, you're going around negative 13 or so. And Jupiter, one of the brighter planets in the sky, in fact, it will be the brightest planet in the sky out tonight, because Venus is now setting below the trees. Jupiter is pushing around a -3 at its highest brightness. And a lot of these objects will change in brightness. The sun is the exception. It's not going to change too much, but objects like planets do change their distance as we go around the sun and as they go around the sun. They're changing their distances, and that does change their apparent brightness from here on Earth. Then we have stars. This star here is Vega, and it hits just about 0 magnitude. Then we have the Andromeda Galaxy. Notice the Andromeda Galaxy comes in just before the faintest naked eye objects. So you can see the Andromeda Galaxy with your eye. No telescope, no binoculars required. You can see a galaxy. Now, it's not going to be super vibrant and bright or anything, not like a picture of Andromeda that you'd see, but you can see it's more than, it looks different from a star, and it's more than just a little fuzz, especially in the darkest of nights. You can see a little detail, some of those arms coming out, at least the evidence for that. Okay, then out here we have the Ring Nebula, and that's just a very basic symbol for a planetary nebula. The Ring Nebula is probably the best, truest example of what a star throwing off its outer layers can look like. And that's exactly what happens. Billions of years from now in our solar system, the sun is eventually going to start expanding, and it will keep doing so. That outer layer will keep growing. And the fate of our solar system will be very similar to something like the Ring Nebula. That's beyond what we can see with our eye, and everything out here beyond what we can see. So why the flip? Why is this not so intuitive? Well, it has to do with how stars were measured early on in astronomy. When people really first started looking up and started trying to apply classifications to these objects in the sky, it was measured in magnitudes, whole magnitudes. So you'd have a first magnitude, second magnitude, third magnitude, fourth magnitude, and that's a ranked system. So your brightest stars are going to be your first magnitude stars. Dimmer stars count up. And so as time went on, astronomy being among one of the older sciences, all that legacy just kept pace. And eventually we ended up having to count back once we really started quantifying these brightnesses. And that's where those negative numbers come into play. All right. A little history there too. Okay, C is for coordinates. And we'll talk about two coordinate systems. The first one is called altitude-azimuth coordinates. And this is much simpler than it looks here in the diagram. All you need to know for altitude-azimuth is you need to know your compass directions. So you got to find north. And you need to know how to measure, which we did with our A of ABCs. So you can see how the compass directions are marked along this azimuth. This is the azimuth down here. So north is 0 degrees, east 90, south 180, and west 270. That's your azimuth directions. And then you have your altitude, which goes from 0 to 90 degrees. 90 degrees is your zenith, the highest point in the sky. So using this system, at any instant in time, you can measure where these objects are. So just thinking about the North Star. North Star is in the due north azimuth direction, 0 degrees. So that's your AZ. And your altitude for the North Star, it changes depending on your latitude. So in our area, it's about 42 degrees. You would find the North Star 42 degrees above the horizon. So that's also a neat way to determine your latitude. If you ever get like really lost, I mean, you'd have to get super lost, have no idea where you are, you can measure your latitude using the altitude of Polaris, the North Star. Well, that's a nice trick. And then there's just this general star on the other side of the sky that, just as an example, you count your azimuth from north, which it's measuring here about 150 degrees, and your altitude about 50 degrees. So this is how we can measure where objects are in the sky at an instant in time. The thing about this, though, is that does change. And it doesn't take much. Over the course of an hour, you'll notice some dramatic change in where those objects are in the sky. So we need another system. And this is where equatorial coordinates come in. And we won't go too in-depth with this one, because as you can see, it's crazy. There's a lot going on. I will tell you that whereas before we had altitude and azimuth, now we have right ascension and declination. The thing there, though, the purpose of this is to map out specific coordinates of objects in the sky that keep up with a system, that keep up with a grid. So let's look at it like this. I have some globes up here. This first one is just a globe of the Earth, your standard globe of the Earth. And the Earth spins, it spins once every 24 hours. And because of that spin, it appears like the star field above us moves. It also appears like the sun moves across the sky. But it will appear like the star field moves and is rotating instead of us. We actually had a great talk last week from Professor Andrew Glenn that got into a lot of the history of how humans understand the sky. It was a really nice talk, and I was at Winter Star Party, so you can go back and check that out. But this gives you a kind of a combination of the two globes. So I'll come down the line and show everyone this one. This shows you the Earth globe at the center. And then the outer globe is the star field. And now, so that star field, depending on what way you look at this, you can have the Earth rotate on the inside, which is truly what's happening, or you can have the star field rotate, which is kind of what it looks like to us. Okay, so I'll come down again. And because of this motion, and we're trying to track this motion, we have this equatorial system that's fixed to the stars. One last way you can think about this too is if you took Earth's latitude and longitudinal lines and pushed them out into space, that's what this system is. So it's taking all these lines you see on this globe and pushing them out to the stars. And then you're able to map exact coordinates for objects. Now some of them will change, like planets are going to move through the star field, so they will change their right ascension and declination throughout their orbit around the sun in our orbit. But stars are going to be pretty fixed. It takes a long time to notice changes in stars through the star field. Okay, so these are important as you learn about some of these tools. You can try out yourself, or maybe you've already tried, like sky simulation software or apps. You'll see all these things come into play, and that's the goal of the ABCs, is just so when you start using these tools and learning more, you know what, at least initially, what those are, and you can always dive into more details.
What is the elliptic?
Oh,
Is that the tilt?
let's go back. So the ecliptic here, this green line that goes around, that represents the path of the sun throughout the entire year. So the sun's going to appear to move through the star field and move through constellations as the year goes on, because we're in orbit around the sun. And that's where that motion comes from. Okay. It's actually a really important line that we will use later, because not only does it represent the path of the sun throughout the year, you can also find planets and the moon along the ecliptic. And we can talk more about why that is in a bit. Okay, let's look at stellarium. Stellarium is the first tool we're going to use. And to download Stellarium or to access Stellarium, you can go to stellarium.org. That's stellarium. It's kind of think planetarium with that, because that's exactly what it is. It's your at-home planetarium. And you can download it for just about anything you want. Just note that the downloadable version is more complex. It has a lot of features. It even has the ability to control telescopes. So that's the advanced version. If you just want to start simple, then you go to Stellarium Web on the far right over there. And we'll just say allow while visiting. That's fine for us. But you can also directly input, if you don't want to use your GPS location, you can input it down here and just do a search. Which is also nice if you're traveling or you just want to see what the skies are like elsewhere on Earth. You can bounce around. There's also Stellarium Mobile, which is pretty much the web-based version, just as an application downloaded for your phone. So it's just as intuitive and simple as the web version. Also, just because I recently discovered it myself, there is a VR version now of Stellarium too. So if you have a virtual reality headset at home, when it's cloudy out and you want to look up at the stars, it's quite nice. And it's also very peaceful because they have some sound effects in there. So nice way to just relax for a bit and see what's out there. Okay, so come right here to the right-hand side, and it gives you your date and time toolbar. This lets you control date and time, so we can skip ahead by days. You can see how the sky changes. Go back to real time. Skip ahead by whole months. So we're in May now, and you can see the sky is much brighter because it takes longer for the sun to set. Now you can skip ahead by whole years even, but we can also just go minute by minute, see how the sky changes. So it's a time machine. You can, I don't know exactly what the limit is on Stellarium Web, but I know on the downloadable version you can go tens of thousands of years into the future. That's how good the model of the sky is. Okay. I will show you also, since we were just talking about the ecliptic, where to turn that on. And why am I blanking on this? Oh, I think it's over here. Settings. So So there is a checkbox for the ecliptic line, and you can map that right onto the sky. So it's mapped out as this red line, and as I mentioned, you can find objects like planets and the moon along this ecliptic line. Reason being, I don't know if I have that poster up here. I guess I don't. When the solar system forms, just after a star is born, before you have any planets, you have something called an accretion disk. And it's shaped like a disk of gas and dust and material that will form planets. All that material will start pulling together. Bigger rocks will start pulling in smaller rocks, making bigger and bigger worlds, and eventually you end up with full planets. Because that's shaped like a disk, they're all roughly going to form along the same plane. And so the Earth formed along that plane. So the sun's going to follow that path in the sky for us. And all the other main planets formed along this plane. The moon did too. So you'll see the moon go through this same arc in the sky. And it makes it kind of convenient, because when you know there's multiple planets out, you can start tracing them together in the sky. And you automatically, your brain's going to start mapping out a real ecliptic. You can't help but connect those dots. Kind of like some of the brighter constellations. So, really powerful imaginary line. All right. So on Stellarium 2, you of course have your compass directions that guide you around the sky. You can also map out the coordinates we were just talking about. And this would be the case with any sky map like this. You can map out the azimuthal grid, which you see is linked right to your horizon. So this is your 0 degree mark for altitude, and you can climb up and look to the zenith in the sky, which is straight up, and that's your 90 degree marker, your zenith. And then as we mentioned before, for azimuth, north is 0, east is 90, south is 180, and west is 270. Okay, and then you can also map out the equatorial grid, which the top, the north end of the equatorial grid is going to just about line up with the North Star Polaris. Because as we think about rotation again, and what that equatorial grid is really trying to do, the Earth spins on an axis, right? That North Pole axis points directly into the North Star. So here's the very powerful moment when we start traveling through time, and we're centered in on the North Star here. Let's just click this. The entire sky is going to appear to rotate around the North Star. And that means the North Star will never rise or set. It's going to stay fixed, just about, at that point in the sky. So even if you go day by day, same thing. That North Star is always at the same altitude in the sky, and at 0 degrees or north, due north. So now we're already in December, and the North Star is still there. So that's why we can use it as a North Star in the northern hemisphere. In the southern hemisphere, they're not as lucky. They don't have a due south bright star. And if we push this far enough, let's see if it'll let me. Oh, no, this one won't let me type it in. Nope. So you might have to try the downloadable version for that one. But if we push this far enough, you'd see Polaris go off track. And it wouldn't be a true North Star anymore. So we kind of luck out right now. Okay. Let's turn that off. We'll come back to Stellarium again, but for now, go back here. And we come to what can we see in our spring skies? So, big one I always start right off with is the International Space Station. And especially as the space station reaches the end of its life, it is going to be most likely brought down in the early 2030s. Now's the time to observe it in the sky over the next few years. So the ISS, it's where astronauts go. If you've heard of an astronaut flying to space, 90% of the time it's going to be to the ISS. That's becoming maybe even less common, if only because private space flight is becoming a thing. So sometimes you hear about even non-astronauts flying to space. But this is a football field-sized object orbiting around Earth a little under 250 miles above us. And it orbits once every 90 minutes at 17,500 miles per hour. It's zipping around Earth. And so at that speed, you could travel from New York to LA in about 9 minutes. So it's moving fast. And here, oh, do we have a question? Oh, yeah.
What powers that?
Oh, wow,
I see the solar
yeah.
panels, but like, what makes it?
Okay, so the nice thing is that once you get in, you'd call the ISS is really in the upper atmosphere, but it's far enough above a lot of air particles and things that once you get it moving, it's mostly going to stay moving. So you would use traditional fuel sources for that to get it up into orbit, and it wasn't all built at once. It was pieced together over time. So that's one thing. The other side of it, though, is that because it's hitting enough air particles every once in a while, they do have to boost it. And that, again, they would use regular fuel sources to do.
It's just pulled by Earth's gravity, so that it doesn't spin off.
Exactly, yeah. It's moving fast enough that it's basically in constant free fall, just like a lot of the objects that we would put into orbit. That's the whole idea is you're falling to Earth, but you're moving so fast this way at the tangent that you just keep going around. So that's, oh yeah, orbital mechanics is complex, but that's like the basic idea of it. Okay, so these are the flyovers coming up over the next couple days. There was one at 4 in the morning, I believe, today. But these are a little bit more convenient for us here. March 11th, 12th, and 12th again. So this is showing you that magnitude measurement. And that's pushing about the brightness of Jupiter. So on March 11th, about the brightness of Jupiter, it starts at 8:39 p.m. in the south-southwest and at an altitude of 10 degrees. What was your 10-degree handy measurement? You remember? I think it was the fest, right? That was our 10 degrees. So that's your altitude for the start of it. Once you get to the highest point, it's 35 degrees up at 8:41. And then look at this, it ends at 8:41. Okay, we'll make note of that. For the next one, which is a little bit dimmer, but starts earlier and gets to its highest point lower in the sky, but it keeps going for a little bit to 7:55. So it doesn't end at its highest point. It starts dipping lower in the sky before it goes out of view. And March 12th, pretty significantly dimmer there, but still bright enough, brighter than the star Vega, starting at 9:27 and ending at 9:29 at its highest point. So what's going on there? Why are these ones ending at the same time, but this one's not? Well, this one's happening earlier. And so there's more sunlight to hit the space station. Keep in mind, it's dark here at these times, right? But the ISS is 250 miles up. So it's still seeing the sun during this time, and it's reflecting that sun down to us. That's what we see when we see the ISS fly overhead. And I think I have a little, yeah, we'll do this in just a moment, who's on board the ISS, but I have a little animation here to show you kind of what it would look like in the sky. It just looks like a moving star. Pretty bright moving star, but just a moving star in the sky. And it's always moving at a constant speed. So you'll never see it like change its speed or zip and zag across the sky. No, it's just going to be a constant arc across the sky at a constant. The only thing that doesn't change is its brightness. So we saw eventually it has to disappear. So as it moves out of the direct sunlight across the shadow of the Earth, it will start dimming, and then it will disappear before it even makes it to the horizon. Yes?
So to use your measurements, then we would, on that date, look at south-southwest and hold our fist above the horizon.
Exactly.
And that's where
Yeah.
it will start. Okay.
Yep, exactly. So at those compass directions, it's always going to start roughly 10 degrees above the horizon. It's the best way to catch it. And that's you may have to account for some trees in your way too, or anything, buildings obstructing. You may not see, of course, until it gets above those. Yeah. Oh, sorry. Yeah. Yeah. Go ahead.
Is anybody piloting space station? In other words, you go up in a plane and somebody's controlling the plane, the direction, the altitude.
No, not constant. It's not akin to piloting an aircraft. There certainly are controls on board the ISS. But no one needs to be helming them at any time. They have certain roles that they play on the space station, but a lot of it is autonomous to some degree, because once it, like we were talking about earlier, once it's in orbit, not much is going to change that. The times where you do have to change its trajectory, of course to boost it in the atmosphere like we said before, and also if you have to avoid some known space junk that's in orbit around Earth. In that case, you definitely have to divert it and expend fuel to do that. But a lot of that is also commanded by NASA directly at mission control. Yep.
How do you determine the difference between a satellite and
So they look very similar. So the ISS is going to be among the brightest of the satellites that you can spot in the sky. So that's a big thing you'll want to look for, is a bright starry-like object moving across the sky. But otherwise, it can be easy to mistake them. So using a website like I got these from, I'll show you. If we go to Heavens Above, this is a great way to track these objects, amongst many others. You can use applications like Stellarium. They also track satellites, but this is a good way to get just a table of flyovers. So we do have to come over here and not be off the west coast of Africa. Probably if I just put Vestal, we'll find it. Yeah. Okay. Oops. Just want to update that. And then you can come to ISS. The other satellite that's very similar in brightness to the ISS is the Tiangong space station, which is the Chinese space station. So then you can see a full list of upcoming flyovers. That's a great way to track. All right. And that's a really important question too, because with more and more stuff getting into our atmosphere nowadays, there's lots of satellites. So it's good to have a place to track all of them. Okay, who's on board the ISS? There is a great website called Who is in Space that I'm going to take you to right now. It's exactly what it sounds like. Right off the top, it tells you who's in space, how many humans are in space. There's 10 people in space right now. And then it breaks it down by mission. So, yes, these two astronauts are still up there. If you know anything about these two, they flew aboard the Boeing Starliner spacecraft last year, and yes, they are still there. So their mission time in space is almost, it's getting close to a year now. Like, we're getting to that point. So, yes.
Is there any indication yet of when they expect to bring these two back?
I mean, last I heard they were really hoping to bring him back sometime this spring, but I've heard that date pushed out a number of times. So, to some degree, it's I really do wonder what they're feeling, just because, like, you didn't plan to be in space for 275 days. But both of them are, as you can tell down here, seasoned astronauts. Sunny especially, and I'm sure they don't mind being in space, except for, like, maybe their families are a little worried. I don't know. But yes.
Monitors their health and their psychological state at any one time.
Yeah.
Yeah,
Yeah.
especially being in zero gravity for a long period of time can.
It has its effects.
It does.
We have a whole set of classes that we especially for summer programs that we get into with students about how space affects the human body, and yeah, so that is a major concern. One of the people that is responsible for the astronauts is Joe Dervais. He's a flight surgeon, and his whole purpose is to understand and assist with the astronauts' health, both here on Earth and in space. So that's the kind of role, the person that would be responsible for that. Yeah, I'm sure, like, with people being in space for this amount of time, on one hand, like, there's data there that's part of the reason why they have these long duration missions. I don't know if that cosmonaut is still in space. I'll have to look as we scroll down here, because he was in space for a long time too, and that was purposeful, to understand better how it affects the body. That's one of the biggest science. You don't want to say, humans are guinea pigs here, but that is one of the things that they're interested in with astronauts that go to the ISS. So then we have this Soyuz mission, which is usually, it's a combination. It's always an American astronaut and then cosmonauts flying aboard this as well. This is part of the partnership, and among the things that makes it an international endeavor. And vice versa too. You'll find cosmonauts flying aboard the American flown missions through Crew Dragon. So these are the three up there right now. And then scrolling, was that, let's see, does it say total time? 177 days. Well, that one cosmonaut may have flown home. He was in space for a while. And then SpaceX Crew 9, which is the American flown missions. And again, American astronaut and cosmonaut. Usually this would be a 4-person mission, but given there's 2 astronauts up there that weren't supposed to be, this was a 2-person flight. Okay. So, like, I guess worst case scenario, they come back with Crew 9, but I think they wanted them down sooner than that. Okay, and then these are who are on the Tiangong space station, the Chinese space station. So this all collectively totals 10 astronauts in space. Okay. And there we go. Ah, we lost it. So we did who is in space. Let's go to solar system.
What was the reason behind? I don't know a little bit of the backstory.
Yeah.
What was why are they left?
The only part I know for sure about it is just NASA determined that Boeing Starliner spacecraft may not have met the risk assessment to actually send them home aboard that craft. I don't know much more than that.
Simply the risk was too high to try to bring back.
Exactly. Yeah. Okay, so let's get into what's there in the solar system that we can see. Now, of course, the sun is out. Well, around here, it's not necessarily out every day, but well, it is right. It's there in the sky. There's evidence for something bright being there. So the reason I always start with the sun, though, is in part because it is going to be responsible for something that we could potentially see in the sky. But more than that, just as a point for solar safety, this is the only object that you can't and shouldn't directly observe with your eyes, with binoculars, with telescopes. Only one that's off limits in that regard. If you ever want to observe the sun, it is something that we're able to do here during our solar events with our solar telescopes. So if you're ever up here, like over the summer, that's a big thing that we do with our summer camps. So students will actually get the chance to observe the sun through our scopes. Because maybe sometimes we'll catch the moon in the sky during our day camps, but more often than not, it's just the sun that we have to observe. And we have our heliostat in the physics lab, and the primary solar scope that we use outside is our 6-inch with a special filter on top. Okay, so we're also, though, in solar maximum, and this is an image of the sun from today. And solar maximum is measured by the average number of sunspots that are appearing on the sun. When that hits its peak, you are in solar maximum, and that happens once every 11 years. You get to that peak of the cycle. So today, there are quite a few sunspots. And this one right here is bigger than the Earth. You can fit about 100 Earths from one side of the sun to the other. So that one's just, yeah, bigger than the Earth there. And it's also facing right at us, which, for what I'm going to show you here, is a good thing. Because when you have those sunspots, they can throw off major solar storms called coronal mass ejections. And all that solar material and solar particles come barreling towards Earth when they're directed at us like that. And while a really big one, which hasn't happened during the solar maximum, a really big one can be scary for us. Not in terms of our biology necessarily, but in terms of our electronics, our communications, and our grid. More often than not, this is a good thing, because you get to see the northern lights come this far south here in New York. Usually they just hang up by the poles. But this was from August 12th of last year. And you can see the beautiful colors on display across the sky. Incidentally, this was also taking place during the Perseid meteor shower, and I will point out every once in a while this is a time lapse, so you catch a meteor right in this part of the sky, right there. You see that flash of a long streak in the sky? That is a Perseid meteor. Not to be confused with all the chaos you're seeing here. All these little things whizzing by, that's something in orbit around Earth that shouldn't be there. Our best guess at the time was that it was a Chinese rocket that blew up way up in the upper atmosphere. And that's why there was all this debris. Because you see how random it is? It's like as if it came from something that exploded. Because otherwise orbits of satellites are going to be very consistent. But you have all this similar material here that tells you it probably came from the same source, and it was probably an explosion. And there was an explosion that day or the day before. So it kind of added a nice effect to it, though. I won't lie that I'm glad we kind of captured that. It's neat. But not meteors. The only meteor is that big streak that shows up in one frame of the time lapse. Okay, so we can see the northern lights. Now there's no way to predict that over a long period of time. We just generally know that we're in solar maximum, so likely we will have another opportunity to see northern lights. I think even just the other day, they didn't quite get this vibrant and this even this far down, but if you were up in northern New York, I think they said at the Adirondack Sky Center, they were spotting them. So be on the lookout for future storms. Let's see how we're doing on time. Okay. Let's go to spaceweather.com. I think that was my next slide, but that's okay. We'll go to this one after. Spaceweather.com is your next resource. Right at the top of their page, they're going to tell you the status of the sun and the probabilities of seeing a storm. And the storms are categorized in terms of these G classes. So it says we could see a G1 storm coming up. That's not quite powerful enough for us to see it. It's around G3 you would want to look for. G3 and above is where we would start seeing it here in New York. It will also give you, this is where that image came from, the most recent image of the sun. And if you come down here, you can explore even further what the status of the aurora and these probabilities that are associated with it. So this is the activity. It's once we get into these upper levels, there's another measurement too called KP index. So when we get into the 5s, 6s, and 7s, that's really good news for us in our northern lights. And you can see the equivalents here for G classes. So it's a good website to explore. At the very least, you can read this blurb, and it gives you a nice summary. Okay. Go back here. We're still in the solar system, so what else can we see? We can see the moon. And just to mention the phases of the moon, one lunar cycle is about 30 days, 29 and a half days to get through all the phases of the moon, from new moon to full moon, back to new moon. Okay, so 29 and a half days. And how do you observe it? Super easy. You look up, you put a pair of binoculars over your eyes, telescopes and cameras, lots of good ways to observe the moon, and all safe. The moon's bright, but it's not going to cause any damage to your eyes, despite what it might feel like when you view it in the 6-inch telescope outside. It's not going to hurt your eyes. Now here's something exciting. Next week, we have a total lunar eclipse. And this photo was from our live stream back on May 16th of 2022, where we captured that eclipse. And that was an excellent timed eclipse. It was really convenient to observe. You didn't have to stay up super late. Unfortunately, this one's a bit of a different story. Before we get to that, very quickly, how do lunar eclipses work? You can think of it as the opposite of last year's total solar eclipse that we saw. We didn't see. Too cloudy. But in that case, the moon was over here on this side of the sun. And with solar eclipses, they end up being far more localized because it's the moon that's casting a shadow down on Earth. And that shadow is pretty small compared to the surface of the Earth. So it's going to be much more localized. Lunar eclipses happen when the moon's on the other side. What would normally be a full moon during a total lunar eclipse, the moon is entering the Earth's shadow called the umbra. There can also be partial lunar eclipses, where it only partially enters the umbra, and there can be penumbral lunar eclipses, when it only enters this area called the penumbra. Best way to explain a penumbral shadow is to look around the room right now, maybe at the shadows of the chairs below you, and notice the very dark, direct shadow that's being cast versus the fuzziness you're seeing around that shadow. It's still dimmer, right, than the direct light hitting the carpet, but it's that fuzzy shadow, that diffuse shadow, that is the penumbra. So when the moon only enters the penumbra, it's going to be a slight dimming, and only deep into the penumbra where you really would notice it. It's the umbra where things really start changing. And that's what's exciting about next week's eclipse, is it's going to fully enter this penumbra, and they're doing a great job in this graphic showing you that red color of the umbra. Because as the moon enters that shadow, it's going to turn red, like we saw here. And you may hear this called the blood moon. Little scarier than intended. So it's all, the only thing that's happening there is the sunlight's coming through the Earth's atmosphere on the sides here. And it's entering a lot of the atmosphere. And then that indirect sunlight is being cast along the umbra. It's kind of like every sunset and sunrise on Earth is projected onto the moon all at once. What color are our sunrises and sunsets in the sky? Reddish pink, right? That's why that color comes on the moon during this time. It's all from our atmosphere. Okay. Here's the timeline for it. Gonna be awake? So there's 7 stages to the total lunar eclipse. This is gonna happen from very briefly on March 13th at 11:57 p.m. and end on March 14th at 6 a.m. So yeah, this is more like the one that happened in November of 2021, which was an early morning event. And it won't be until about 2 a.m. to 2:30 a.m. where you'll really start noticing the impact of the eclipse. And then total eclipse is from about 2:30 a.m. to 3:30 a.m., almost actually more than an hour there for totality, and then concluding at 6 a.m. So we will be live streaming this somehow. I still gotta, it ends up being like a super busy weekend next week too, with events and programs, but we're gonna find a way to do this. So at the very least, you can enjoy it after the fact. And usually we put together a time lapse too of the event, so you can watch it even play out over the course of a minute. So you don't even have to sit through all this. If you want to see the full breakdown, timeanddate.com is a great place to go. That will guide you right through all these stages. You can even scrub through the event to see how it's going to play out, what direction the shadow is going to appear, and so on. Okay. I always like, whenever we have an eclipse come up, I always like to show this picture, at least for a lunar eclipse, because this is a compilation of images put together to show the shape and size of the umbra during a total lunar eclipse. You can see the Earth's shadow and how big it is compared to the moon. That is the Earth's umbra here. And then beyond that is the penumbra. And this was an APOD image, an astrophotography picture of the day image by Lishan Wang. You can look that up. It's just a really brilliant image. Okay. What planets are out? Still in the solar system here. 2 visible planets this spring. I had to be careful because there technically are a couple more planets out right now, but we're really still in the winter. Even that lunar eclipse is still going to happen in the winter season. I thought it was important to mention there because it is a recent upcoming event, but for the most part, in the spring, we just have Jupiter and Mars. If you want to observe Mercury and Venus, you have a little time, but they're going to be drifting closer and closer to the horizon over the coming days and weeks, so there's not too much time for those objects. Jupiter and Mars, these were both taken at Kopernik even with this image of Jupiter, you can see Io, the shadow of Io, and Io itself. And that's a moon of Jupiter, one of the big moons of Jupiter. Okay. We will briefly show you the planets in the stellarium. Back to the web page here. And we gotta make sure we're still... Yep. So at 9 p.m., what planets are out? Like I said, Jupiter and Mars in the later evening hours. If we back up the clock, you will see Venus and Mercury. But if we go ahead a few days, you'll see, oop, there comes the sun. Skip ahead. How Venus drifts day by day closer and closer to the sun. And if you have really good horizons, it's kind of neat because Venus will kind of hit this point where it's switching over from an evening object to a morning object. But that's the thing, is this, if you want to see Venus after this month, it's going to become a morning object, a morning star, as you may hear it referred to, versus an evening star. If you've been seeing a very bright object in the sky where the sun has set in that western direction, guaranteed that was Venus. I saw it coming up the hill today, breaking through the clouds because of how bright it is right now. And a part of the reason why it's so bright, it's super close to us. But if we look at the shape of it, we gotta go back, click this, there we go. Looking at the shape of it right now, here's where we can use the telescope feature of Stellarium, center, zoom. It's super bright right now. It says it's a magnitude -4, brighter than Jupiter. That's all it is, though. It's just this tiny little crescent. Pretty amazing. And that brightness is because of how close it is to us. Okay. Back here. We're going to close things out with deep sky objects. These are your star clusters, your nebulae, your galaxies in the sky. And the first thing I'm going to mention here is not necessarily a true deep sky object, but where you'd find a bunch of them. And that's the Milky Way, which is a huge structure across the sky. It's our galaxy that we live inside, that the sun is a part of billions and billions of other stars within it. So you can find a lot of deep sky objects in this. This is not an evening object yet. This is an early morning object, but spring is the first time where we're going to start to see the bright part of it again, the bright core. And that's going to come in handy later when we talk more about galaxies here in just a moment. So Milky Way, coming up this spring, and then into the summer, you'll see it in the evening hours. The Orion Nebula, we're heading towards the last opportunity this season to see the Orion Nebula and the constellation Orion. When I give you your star maps later, you'll see Orion on that. We have the Pleiades, the Seven Sisters. This is an open star cluster, and again, more of a wintertime object where it's really high up in the sky in the evening. But now they're going to start drifting to the western sky, where they will eventually get too far below the horizon. We'll have to wait till late summer to start seeing them again. Okay, so there's a couple that are closing out, but it's also galaxy season for spring, where we can see so many galaxies. This is the best time of year to see galaxies in the sky. So something like the Virgo cluster, which is a cluster of galaxies. Every single one of these fuzzy things, even this little dim one back here, or these ones here, they're all galaxies, each with billions and billions of stars, and billions of planets. So you can see something like the Virgo cluster. The Whirlpool galaxy. I think this one was the one taken on the 20-inch. telescope here at Kopernik, and this is galaxies colliding together, a smaller one here and a bigger one here. And one of the neat things you can capture when using a camera on this object is you can see all this dusty and starry material around the smaller galaxy and how it's getting almost like it's getting thrown around. It's really diffuse out here as the bigger galaxy works on absorbing this. This plays out over a long, long period of time, but it is an example of how everything's in orbit. And when a smaller galaxy comes near a bigger galaxy, things are going to happen as they orbit around each other and one gets absorbed. Here's the Pinwheel Galaxy, again taken through our 20-inch telescope. And this points out a supernova that was happening in 2023 in one of the spiral arms. That star right there that we captured it was probably either George Normandin or Patrick Manley that captured this picture. They're part of the Astronomical Society here. That was not there before. But then, when that supernova went off in this galaxy, you could image it, and you could even see it with the eye. It was almost brighter than the core of the galaxy itself. In fact, to me, when I observed it, it looked distinctly brighter, but that could just be because of how diffuse this was. Yes?
How far away is that at night?
Ooh. Do you happen to know, Sasha? I don't know offhand how far Pinwheel is.
I just always like to note that when we see something like that, it happened a long time ago.
Yeah, exactly.
And we're just seeing it now, however many years after the fact that it happened.
Absolutely.
So it may or may not still be there, even as we're seeing it, because even at light speed, it's so far away that it's taken lots of years to get here.
It's yeah, we're looking back in time here. Yeah.
None of us were here
25.
when that happened.
Okay, so Sasha here looked up that it's 25 million light years away.
5 million light
So you're looking 25 million years. All right, next up we have Bode's Galaxy. Another very pleasing galaxy to observe. You have these very distinct spiral arms jetting off of it. And then this is an example of an irregular galaxy. It's called the Cigar Galaxy, or M82, and it's not a spiral galaxy. It has an irregular structure to it. Think of it more as just like a star cloud. It does not have that spiral arm structure to it. Now, one thing you've noticed through each of those galaxy images is that M classification. It's actually part of a catalog that French astronomer Charles Messier, who was an 18th century astronomer, he came up with this catalog of 110 deep sky objects, not just galaxies. In fact, he didn't even know what those were, that they were galaxies with billions and billions of stars. It was a catalog of galaxies, nebulae, star clusters, and things that are not comets. That's what he was cataloging them for. He was telling other astronomers, you may see this in the sky. You may think it's a comet. It's not a comet. Don't mark it down as a comet. That was the purpose. So he was a comet hunter. But there's something called the Messier Marathon, where there's usually a date or two throughout the year around new moon in the spring, where we can observe all of them, all 110. But it usually is only a day or two. So this one is March 29th into the 30th during that new moon. And if you're willing to stay up all night on that day, you'll catch some of them. If you only want to hunt for like the evening ones, you could do that. But if you want to catch all of them, you gotta stay up all night. Because there's a lot, like I mentioned earlier, the Milky Way has a lot of Messier objects in it. You gotta wait for that to rise. And in March here, it's not gonna rise till after the morning hours. There's a website you can go to. If you just do a Google search for the Messier Marathon 2025, you'll get to a full page that gives you guidance on how to find all these objects. But that's a big spring event that a lot of our, those in our Astronomical Society and a lot of amateur astronomers are always interested in. So great way to start hunting for these objects, even if you don't catch them all the first time. A lot of them are good binocular objects too. All right, we're going to skip that part. There is a search function in Stellarium at the very top, so if you ever want to find something like those galaxies, type in a search and it will go right to it. Some observing tools you can use. You can go to stellarium.org like we did earlier to download or view the web version or get access to the mobile app. If you want to explore other apps, and maybe you have one of these on your phone already, you can download Starwalk, Sky Guide, or Sky Safari. These two are very similar in what they, in their simplicity. They're very simple to use. And a lot of these apps also have the compass function, where it will use your gyroscope and your compass in your phone so that you can raise it up and get an estimation of what the sky map is showing versus what's really in the sky. So that's handy. It's mostly just aesthetic differences between these two. Sky Safari is a more advanced one, and it does have different tiers. This is an example of a mobile app that you could use even up to the level of controlling your telescope. So that's a super powerful one, and the highest end version of it is a paid app. So I would start here, and then if you get really into astronomy, jump over to Sky Safari, because that is a powerful application. The last tool I have for you is your smartphone. Beyond those applications, you can use your smartphone to take pictures of the sky. And this is something every skies program that we do, I encourage you, even if it's slightly clear out there when we end the program, take your phone out, get it into night mode. Usually it's going to be automatic, that it sees a dark sky or something dark. It turns on even if you're just trying to take a picture in a dark room. And at least on iPhone, you'll see it as this little moon toggle. And on here, you can also swipe up and adjust the exposure time. It works best on a tripod when you're taking them, because then you get access to 30-second exposures, where you can really start collecting a lot of this starry detail. This one on the left, though, was a handheld image. So with just handheld, I think this was probably a 10-second image, you can see the constellation Orion. Here's Betelgeuse right there. The other shoulder of Orion. These three stars are the belt, Orion's belt. The legs come down here. And this, you can see right there. The arrow's not, let me just use my laser. That is the Orion Nebula. So you can capture, even just a handheld image, you can capture the Orion Nebula in the sky. Really powerful. Here's one related to the event next week. This was captured on a smartphone as we were streaming the total lunar eclipse. So you're capturing a very dark room that's just filled with some dim red light. Even then, it's picking up a lot of detail in the telescope. And then it's looking out the dome at the dark sky and doing a good job of picking out some stars up here. But most importantly, it's picking up that red moon in the sky. And just like that image we saw earlier, this is that same moon. So part of it is brighter, and part of it is further into that shadow, that umbra. Okay, so you can do a lot with your phone. And of course, I always end this program with clear skies, and 90% of the time it's not clear skies. But my hope is this spring we will have some lovely clear skies to observe. And you can look for some of these items. The thing I'm going to send you home with today is a sky map. And you can download these sky maps for free online. So they go month to month. They release one every month. You go to skymaps.com and you can get access to it. The map itself, it's just a static map for the month, so it will show you planets. It's not like a star wheel that would only show you stars. So you will get to see the planets and their average location for that month. And be careful to know if you do download these later, there's a northern hemisphere, an equatorial, and a southern hemisphere. So make sure you're always downloading the northern hemisphere. It shows you events on the left-hand side. And if you flip it around, it will show you different categories, things like tips for observing the night sky, your astronomical glossary, telescope objects, binocular objects, naked eye objects. So things to look for this month. And you can download more for the coming months. So definitely pick one of those up on your way out. At this time, I am happy to take any questions before we close out the show, either on the live stream or in the audience. Yes?
How are names determined? Like, when we look at something, how would they come up with a term to use?
Yeah, that's a great question. And what's amazing about the field of astronomy is because of how old it is. We find that a lot of it is based in mythology because humans have been observing these objects in the sky for a very long time. So things like the planets are going to take on, especially the visible planets, are going to take on Roman names. Now, of course, that is a decision that's made in the field of modern astronomy. In modern astronomy, we use a lot of Greek and Roman mythology. That is a choice, and thankfully we are branching out when naming things, especially things like dwarf planets. They're taking on names from other cultures, so that we're not just stuck in that one space. But yeah, exactly. Yeah, and it's just to be ultimately more inclusive, because it's not just the Greeks and Romans that observe the sky by any means, right? Everyone, every culture in human history couldn't help but look up. I mean, especially back then, there was no light pollution. You could just look up in the sky and see the Milky Way all the time. Here, if you're down in the town of Estill or in Binghamton, you won't see the Milky Way. You have to come up to a dark sky site like Kopernik to spot it. So yeah, there's different cultures. That's another feature of Stellarium, is you can change the culture, the star cultures, and see the names of those objects under a different culture beyond Greek and Roman. So, but it just so happens in astronomy, when we name something, when we use a name, it does tend to be that mythology. Mm-hmm. Yeah. Any other questions in the audience? Perfect. Any questions on the live stream? All right. Well, at this point, remember to pick up your sky map before you head out, and maybe look to see if the telescopes are fixed on something. I know things were breaking through. I saw Orion when I first got up here. So we'll see if the telescopes are behaving. And if you do not get to look through a telescope tonight, and you're also not a member, because members get in free on Fridays anyways, we'll give you a complimentary pass to come back. So make sure you check in with us before you leave about that. Okay?
How many nights are you open?
So with the exception where we have any staffing issues or problems that come up from now to mid-December, we're open every Friday night. We also will be open for select events. Like first one that comes to mind is the Perseid meteor shower in August. We're usually open for a few days in a row for the Perseid meteors. So for big astronomical events, we're open, and otherwise every Friday night we're open. Okay. All right. Yeah. Thank you all for coming tonight. And yes, clear skies in the future.